Oh, hi everyone. I'm Bhaswati Choudhury. I am going to talk about surface dielectric barrier discharge plasma decontamination. This is on the work based on projects that I did in Surfplasma as a research scientist in collaboration with University of Florida, Gainesville. So to start with, this presentation is organized as follows. I'll first start with the introduction, move on to motivation and objectives, then talk about the main research on enhanced surface dielectric barrier discharge decontamination, and finally end with the conclusion. So let's start with the introduction. First, let's talk about what is dielectric barrier discharge plasma. So when two electrodes separated by a dielectric barrier, when we put a high enough AC voltage across such two electrodes, plasma is formed on the surface of the dielectric barrier or in the volume separating the dielectric barrier and one of the electrodes. Based on where the plasma is formed, it's classified as surface DBD plasma or volume DBD plasma. This research is mainly focused on surface DBD plasma, but can be extended to volume DBD as well. Now moving on to SDBD plasma reactors, here is a generic SDBD plasma reactor where we have an exposed electrode, a ground electrode, separated by a dielectric barrier. When we give a high enough AC voltage, there is plasma formation on the surface of the dielectric barrier. Now, the plasma formed here is basically a neutral soup of various particles like ions, electrons, radicals, charged atoms, neutral atoms, as well as molecules. What happens when plasma forms in such a situation is, first, there is formation of induced flow. How this happens is when accelerated charged particles in the plasma area collide with neutral gas particles and there is an elastic momentum transfer, elastic collision. This leads to momentum transfer leading to an induced flow, which happens around the area where the plasma is formed. Now, due to this mechanism of SDBD reactors, they are often used as flow control devices to control airflow around surfaces where the DBD reactors are placed, and they have applications in aerospace industry and noise control. The second mechanism that occurs is the formation of reactive chemical species. This happens when inelastic collisions happen between particles, radicals or charged particles, and new reactive species are formed due to these collisions. One such major species formed is ozone, when plasma is formed in oxygen-rich environment or in atmospheric air. Because of this mechanism of generation of species like ozone, DBD reactors are also used as ozone generators to decontaminate its surface air or water. Now, ozone is a powerful decontaminant because of its high oxidation potential, and it destroys microbes as well as pollutants through a series of oxidation reactions. The main focus of this research is to combine SDBD flow actuation and ozone generation to increase decontamination efficiency. Although DBD reactors have been widely used for flow control and ozone generators separately, the flow control mechanism or unique characteristic has not been implemented in the decontamination area, and that is the focus of this research, to kind of use that flow actuation to distribute ozone to achieve targeted decontamination. This brings us to the motivation and objectives. So let's start with why are we interested in DBD decontamination in the first place? There are a lot of traditional methods available for decontamination like autoclaves, UV treatment, chlorine treatment, as well as radiation treatments. But these methods have disadvantages like high processing temperatures, material damage, toxic byproducts, residuals, as well as high exposure times. Because of these disadvantages, DBD has turned out to be an attractive alternative with advantages like low processing temperatures, low material damage, less toxic byproducts and residuals, as ozone usually decomposes to oxygen in time. and even less exposure times required for decontamination. Due to these advantages, just DBD decontamination has found its applications in various industries like air and water purification, food preservation and storage. Here is an example of how it can be used to extend shelf life of various produced products. This is a project we conducted under NSF at Surfplasma. And the other use is for sterilization of materials, especially materials which are sensitive to high heat, high humidity, or toxic chemicals. One such example is the spacecraft assembly facility clean room that are used to decontaminate spacecraft components. The problem there is the approved methods of dry heat microbial reduction and vapor phase hydrogen peroxide cause thermal and chemical damage to highly sensitive electronic materials, which is why there is a need for an alternative decontamination method, and DBD has so far proven to be a good alternative. Although there are a lot of advantages of DBD decontamination, their application have been limited by high energy consumption, bulky equipment size, as well as high ozone dosage requirements. Research done so far on SDBD decontamination, or surface dielectric barrier discharge decontamination, has been on 3 different focus areas. First, researchers have studied how different plasma generation parameters affect the plasma formation itself, like voltage, power, and dielectric material used for the formation. The second research focus has been on ozone formation and ozone generation, which is basically the study of various species reactions that occur within the discharge to generate ozone. The third focus area has been on the decontamination spectrum as to what can DBD decontaminate, and it has been proven successful against a wide range of microbes like bacteria, fungi, virus, as well as pollutants like VOCs and VVOCs. Now, the objective of this research is to investigate targeted decontamination using SDBD flow actuation and ozone generation to maximize ozone utilization. In other words, to use most of the ozone generated by the DBD reactor by using the flow actuation that comes with it to reduce the exposure time and required ozone dosage, and this will in turn reduce energy consumed by the reactor itself, which is dependent on the time the reactor is powered up. In addition, what we can do here, if we are able to achieve targeted decontamination, is to have an inbuilt distributing mechanism for distributing the ozone generated inside the equipment, the ozone generator itself, without having to add an external distributing agent. This will lead to reducing equipment size. Now, these 2 factors will in turn help in overcoming the limitations of high energy consumption and bulky equipment, and even lower ozone dosage requirements. Moving on to the main research topic, that is enhanced SDBD decontamination. Again, to repeat it, we are trying to use the flow actuation characteristic of the SDBD reactors in addition to the ozone generation to kind of distribute the ozone and achieve targeted or distributed decontamination. So before starting, let's understand the SDBD flow, how it is generated. So going back to the linear reactor that I had shown before, here we have the exposed and the ground electrode. And when it is powered up, the resulting airflow is from the exposed to the ground electrode. Note that if they are not asymmetrically placed, there will be no airflow. So what happens is for a linear reactor, here is the top view. The flow goes from the exposed to the ground electrode, and here is the flow visualization of the wall jet that results from powering up a linear reactor. Here is the reactor, and we have this induced wall jet parallel to the reactor surface, kind of 2D with respect to the whole volume presented here. Next, we have the comb reactor configuration. This can be seen as a combination of various linear reactors, which results in flow structures because of interaction of various flow induced by all these electrodes with respect to the ground electrode. Research has found that the 3 main flows induced by the comb reactor is one is the main flow, which is a wall jet coming from the shaft towards the teeth tips. And that's the main wall jet. And then we have two secondary flows, which are also wall jets, but with lesser velocities going away from the shaft and the teeth. Here is the smoke flow visualization showing the same. Next, we have the fan reactor configuration, where the electrodes are designed in the in imitating of an actual fan. But keep in mind that these are just the electrode designs. There are no moving parts. When we put the when we power up this reactor, the resulting flow has been found to be similar to that of a fan, where air is sucked out from the surrounding region and pushed upwards and outwards to the help of various turbulent structures formed near the reactor surface, as you can see in the small visualization presented here. Now, the main idea behind using these two reactors, the comb and fan reactor for the study, is that both of them result in very contrasting flow structures that are formed. So to understand that better, we go to the next slide. What we want to see here is how these contrasting flow structures result in contrasting spatial ozone distribution and decontamination distribution, which will be the next few slides. But let's look at the flow a little bit more. So here is a comb reactor, and if we look at it from this angle through a plane sliced right in the middle here, we will see the main flow that goes from the shaft towards the teeth tip close to the reactor surface. And here we can see how the particles move from in that wall jet. This is very near to the reactor surface. The overall flow generated by the comb flow is shown here in this smoke flow visualization video, where we can see the two secondary flows coming out from the shaft tips. Now, in contrast, if we look at the fan flow, this is a flow a simulated flow near the reactor surface. And as here we see the turbulent structures or the vortical structures formed near the reactor surface when this is powered up. The overall flow of the fan reactor is shown in the smoke flow visualization. And as you can see, there's a lot of turbulent structures near the surface, and the flow is going upwards and outwards. If you compare it to the comb reactor flow distribution, we see that the fan reactor really results in a more 3D flow structure than the comb reactor. This difference will be used to explain spatial ozone distribution and decontamination distribution, resulting in targeted decontamination. So before going on to the results of those, let's talk about the experimental setup used for this study. Here is the reactor power supply, where we used a signal generator and an amplifier to provide the high AC voltage required to power up the two reactors. And then we have voltage and current probes connected to an oscilloscope to measure the voltage and current. This was done to make sure that the input parameters were adjusted such that the two reactors were run at the same power levels of around 1 watt. This is the experimental chamber that was used for ozone measurements as well as decontamination measurements. The same chamber was used for flow simulation. The chamber dimensions were used for flow simulation measurements as well. Here is the setup for decontamination measurement, where contaminated coupons with bacterial quantity of 10 to the power 5 CFUs per coupon. CFUs are colony forming units. It's a unit to quantify bacterial population. So the coupons were contaminated and placed in two planes inside the chamber with the reactor fit inside it. And in the two planes, the coupons were placed in a 3x3 grid as shown here. So we had a total of 18 points inside the chamber where decontamination was measured, and ozone was measured in those same points or planes to kind of relate how that works. Moving on to the next slide. Here are the results of the spatial decontamination distribution observed inside the experimental chamber when the two reactors were powered up for 3.5 minutes. The test organism used was E. coli. Now let's look at the results from the comb reactor here. at plane P2, we see the spatial decontamination distribution resulting from the comb reactor. What we see here is a biased decontamination towards one side of the chamber, which corresponds to the main flow where the flow goes from the shaft towards the teeth tips. We will see that in the following slides, how it relates to the flow. But for now, what we can see here is a biased distribution. Same thing goes for plane P3, which is caused by the comb reactor. The decontamination here is also biased, but a little more uniform compared to P2, which can be attributed to the effect of the chamber walls, especially the roof of the chamber, helping the flow to distribute more evenly in that plane. In comparison, when we look at the decontamination distribution resulting from the fan reactor, we see a more uniform decontamination in both planes P2 and P3. Now, the uniformity of decontamination can also be quantitatively understood in terms of standard deviation. As you can see, for the comb reactor, we have high standard deviations in both the planes. That is how uniform the decontamination is throughout that plane. And for fan, we have a lower standard deviations, meaning that it is more uniform in comparison to the comb. Now, what does that mean with respect to decontaminating a surface or an object in the chamber? Imagine a surface that is contaminated and needs to be decontaminated is placed in plane P2 to be decontaminated by the reactors. If we use the comb reactor, what will happen is it will decontaminate certain parts of that surface more than the other parts. So if you want to decontaminate the whole surface, we would need to power up the reactor for more than 3.5 minutes to make sure that the other points are decontaminated as well. What that means is more ozone concentrations, more exposure times, more reactor power consumption. But if we use the fan reactor instead, what we are seeing is that we are achieving a more uniform distribution, which means that in 3.5 minutes or a certain exposure time period, the fan reactor will uniformly decontaminate it. So we can be done with decontamination in that time period. And we do not have to wait for all the points to be decontaminated as in case of the comb reactor. So that is the whole point when I say maximizing ozone utilization. Looks like the fan reactor is using more of the ozone produced and distributing it evenly throughout the plane, which can be corresponded to having decontaminating a surface placed in plane 2 more efficiently. Now, to relate this to ozone distribution, ozone measurements were taken in the same 2 planes and related to relate them to the decontamination distribution observed in both the planes. In plane 2, here's a video showing how it changes in the same exposure time of 3.5 minutes. As we can see, the comb reactor is very biased towards one side, whereas on the other points, there is not much ozone reaching, which can be attributed to the biased decontamination that we saw in the previous slide. As for the fan reactor, there is a more uniform distribution, resulting in a more uniform decontamination. To quantify this relation between spatial ozone distribution and spatial decontamination distribution, we did a statistical analysis where we found out the correlation value between ozone concentration at a particular point and the decontamination achieved at that same point. So using all the data points for both the reactors, we found a p-value of less than 0.001, which means that the relation is significant between ozone concentration and decontamination when measured in a spatial area of the chamber, a plane of the chamber. So the idea here is so if we know how the ozone is going to be distributed, we can know what the decontamination distribution in a certain space will look like because they match pretty well. But the problem here is if we are going to make a device for sterilization or disinfection, measuring ozone concentrations and coming up with plots like this is very experimentally expensive as well as time consuming. So the next idea was to simulate the ozone distribution generated by the 2 reactors in the chamber. Here we see how the ozone distribution looks at 10 seconds of powering up the reactor. and we have both experimental and simulated data to show the difference. So in figures B, C, you can see how the comb reactor, for the comb reactor, there is a biased ozone distribution more towards one side, which corresponds to the main flow. Whereas for the fan reactor, at 10 seconds, what we are seeing is there's more concentrations at the center, which is distributed outwards towards all the walls as time goes by. Now, these are surface plots if you look from the top. And again, we are seeing the bias side, but for the fan, we can see how the ozone concentrations are initially formed at the center. And because of the flow, it will get distributed uniformly towards all the chamber walls. So the idea here is to predict decontamination distribution with simulated ozone distribution, which is more economical than actually measuring ozone, but still computationally expensive because it involves simulating reaction mechanisms, which can take a long time and also a lot of CPU power. So the next idea is, what if we can relate flow distribution to decontamination distribution instead of going for ozone simulation? So here are flow simulation distribution presented for the fan. This is the fan, and for the comb. Here we can clearly see that for the fan, these are the velocity contours where it generates here, and then the velocities kind of go outwards towards all the chamber walls. In case of the comb reactor, however, we see the main flow going from the shaft towards the teeth tips and the two secondary flows that occur as well. So there's more biased distribution here, which corresponds to the decontamination distribution that we observed below. To understand or to relate the flow distribution to ozone distribution quantitatively, here are some line plots. These are all at 10 seconds of firing the reactor. And as we can see for the fan reactor, in both the directions, we have high concentrations at the middle, and the velocity contours show that as time passes, it will carry it on towards all the sides. Whereas for the fan reactor, we have high ozone concentrations at one side of the wall because of the main flow that goes from the shaft towards the teeth tips. And in the other dimension, in the Y dimension, there's hardly any ozone concentrations compared to this, which corresponds to this direction here. So the main point here is we can predict decontamination distribution with simulated flow distribution, which is computationally inexpensive and can be a huge design implement or a huge contributor in designing devices which use different configurations of DBD reactors to get targeted decontamination, to make sure we are targeting certain spatial points where the object or surface will be placed for decontamination depending on the application. To conclude, what we saw here is we saw SDBD decontamination distribution using two reactors with very contrasting flows. For the fan, we saw a more uniform distribution in both the planes of the experimental chamber. Thus, it will uniformly distribute objects at a certain exposure time. Whereas for the comb, it would be biased and opposite. Then we saw the SDBD ozone distribution, which was collected experimentally, and how they differ for the fan and comb. For the fan, it generates at the bottom, at the center, and then distributes uniformly. For the comb, it generates at the reactor, but is pushed mostly away towards one wall. This was quantitatively related with the Pearson's correlation value, which showed a significant relation between ozone distribution and decontamination distribution. Then we saw how we can use flow simulations to predict decontamination distribution. This can be used to design SDBD reactors for targeted decontamination for various applications. Finally, we come back to what we started off with. The goal was to increase ozone utilization or maximize ozone utilization, thus reducing required exposure times, required ozone dosage requirements, as well as energy consumed by the reactor. In addition, the fan reactor also gives us the way to have an inbuilt distributing mechanism without adding an external distributing agent, which will help reduce equipment size. Applications of this research is in surface sterilization, especially in areas like interplanetary protection and space research or food preservation, where we want to have less ozone, that is by maximize ozone utilization, and we want to decontaminate at low processing temperatures. On the right here, we can see the compact portable plasma reactor that is a very lightweight, compact electrical unit that can be used to make decontamination devices. Currently, or for the past 1 year, we have been working on creating such sterilization device for combating COVID, as well as for space applications, where we need decontamination method, which are not traditional. So we have worked with COVID virus and we have successfully killed it. So we are on the way there, as well as for NASA, we have been working with some of their species and how we can implement it in their space projects. So with that, I will end my presentation and I'm ready to take any questions.